So I'd like to introduce John Iversen, not Iverson.
Or Iversen.
And John, I think, was at the Neuroscience Institute, and then he joined SCCN at INC 2013 to do some great mobile brain imaging experiment. And then I think 2 years ago, you left for McMaster. So you're going to tell us about that?
Yeah.
You have it.
I do. Is this working? Can you hear me?
Yeah.
Okay, great. Well, thanks, Arno. Really appreciate the introduction, and thank you for inviting me. I was surprised and very, honored and pleased to be a part of this. What's that? I have, yes. Thanks for checking. Yes, no, it's a real pleasure. So, I was actually in Berlin with a collaborator of ours, and this was an opportunity I didn't want to miss. So I feel like I'm very grateful that I was part of INC for the years that I was here. So this talk has kind of morphed a bit, and I think originally the idea was to reflect on what INC has meant to me and visions from the future. So I've kind of kept that as part of the talk. So it's a little bit different from the title, but I'll call it Music Brain and INC. And me.
I'm a INC.
Okay. Yeah, so in the time, the decade I was here, as Arno mentioned, we did a lot of work with MOBI, mobile brain body imaging. And I'll talk a bit about that. That's something, if you don't know, that was created at SCCN and INC, and it's really a way to study the brain doing what it does best, doing naturalistic activity in the world. Also some methods, and at the end, I'll talk a bit about some ideas for the future that we're thinking about at McMaster. Well, I thought I wanted to think about, what was the INC experience for me and what really characterized it. And when I joined, I guess the first thing I felt was very welcomed. It's a very welcoming atmosphere, and there were many opportunities to get involved. TDLC was going strong. There was EFRI project, and many other aspects. The interdisciplinarity, of course, was extremely attractive, and I think because of that, especially SCCN became this international gathering point of scholars from all over the world. And I think thing that characterizes INC is this synergy between building tools and using tools, which I think is very productive. At the time, at least, I thought the funding model was really ideal. This kind of combination of a foundation grant that provided stability plus project-based grants on top of that. And then certainly Scott was extremely welcoming. My interest in the brain, 10 years ago was not as common, and Scott was welcoming. Together, we started UC Merci. It was kind of a UC-wide collaboration, and also TDLC had some music and brain. So mobile brain body imaging, the idea is to collect multimodal data on humans doing real-world activities. This is something that Scott and TP and Klaus Graf, Dan Ferris basically coined this whole idea very ahead of their time in 2009. So I'll talk about a few projects that I was involved in doing MOBI here. And then, of course, it's been mentioned before, but the tools from SCCN are used throughout the world, kind of with EEG Lab at the core, but many other essential tools for synchronizing data, collecting multimodal data, analyzing, and then most recently, all of this, online big data neuroinformatics work. So, being here and having that at our fingertips, I think is a great strength for visiting scientists. So the first project I'll talk about briefly is a study of navigation. And this actually I saw in someone, maybe Terry showed the slide from the 20th anniversary, and there was a demo of this project then. So that's actually predates me. I kind of inherited, this is the first project I kind of inherited when I got here. And the basic idea was to use augmented reality. The MOBI lab downstairs is a large room with motion capture cameras. And so you can create a virtual maze, creating virtual walls that are sensitive to touch. So you're tracking the location of the hand, and then you can create sounds when you approach virtual walls. So then we can study navigation. And so this is kind of the idea, EEG, streaming EEG, so it's wireless, motion capture, and directional audio.
Yeah, I see it.
And ICA, yes,
There's a lot
get to
of
that. A lot of motion artifact, yeah. So, and then this was collaboration with Mobilab in Germany. So they did kind of a visual maze, we did an auditory maze. So this is kind of some of the sort of behavioral data that we get out of it. This is showing somebody navigating the wall. So they're basically doing what you would do, trying to find your way around in a dark room, an unfamiliar room. And you can see various events up there using head tags, which is another important SCCN invention, a way to annotate, richly annotate events. You can see we can track the person's movement through the maze and all the wall touches. The idea, which I think was Scott's originally, is like navigation is normally kind of a very free field visual flow phenomenon. You can take in a whole room at a glance, and that's very hard to study for EEG, right? So the idea behind the audio maze was to really discretize and atomize the gathering of information about the space. So you're blindfolded. Each touch is like a binary event. Like there's a wall there, there's not a wall there. And so we analyzed those wall touches to start with. The basic idea was to try to find signs of moving from an egocentric reference frame, like there's a wall to my left, there's no wall ahead of me, to a more map-like representation. So we had people run the mazes, explore the mazes 3 times, and basically compare the initial processing and later processing with this model, essentially sensory input going to parietal cortex for multimodal integration. Klaus Grauman has proposed the retrosplenial complex as an important area for kind of combination of ego and allo information. So the basic hypothesis was that we would see, changes in the weighting of input initially from parietal towards retrosplenial, as well as additional information flow between retrosplenial and parietal cortex as we transfer from egocentric to allocentric. Okay. So then this is a movie that Makoto Miyakoshi, who is another postdoc at the lab, prepared. So this is basically using something called causal flow or information flow analysis to look at kind of how information is flowing between different parts of the brain, identified using ICA to separate out brain activity from motor activity and other artifacts. So each of these flashes is a moment of basically computational information transfer between these regions. What that means, we're not studying the actual connections. We're just saying that one signal has information that can predict another signal, and we call that information flow. And to break that down briefly, you can look at, so this is comparing trial 1, which we propose would be more egocentric, to trial 3, more allocentric, more map-like. And you can find connectivity that is greater in trial 1. So that might be greater in egocentric, and other connectivity is greater in trial 3. So for example, the sensory input from posterior visual areas moving forwards was greater in trial 1. Whereas some of this additional information, say, in different areas was decreased. So, in kind of conclusion for this study, sensory influence decreases with learning. And that's somewhat in line with this prediction that we'd see reduced sensory input to parietal regions. And then visual spatial imagery and memory influence increases with learning. So, yeah. Okay. blindfolded, and that's a good point. I probably should have put that slide in, but we were analyzing the wall touches. And in fact, there was very strong visual response to the wall touches. Excuse me. To the extent that essentially the visual version of the maze and the auditory version of the maze showed very similar responses to wall touch. And many people kind of talked about seeing, when they had their eyes closed and they're feeling the walls, they did develop a visual representation. So a second Moby experiment was juggling, which is the idea, let's study motor learning with a task that's a little more complex than like reading, which is kind of the dominant paradigm in the field. But juggling is also less complicated than dance or other creative activities, kind of in this sweet spot, we thought. And this is really a project together with a group in Japan, but really Hiroyuki and Scott came up with this project. And the work I'll show was largely Hyun-suk, who was a postdoc in the lab. So again, basic Moby setup. The only difference here is we have balls that are illuminated and we're capturing with a camera, something like this. So the basic outline of the project was to try to understand what juggling skill is and how juggling skill is comprised of multiple sub-skills. Like, of course, throwing accuracy is essential for juggling. Predicting the ball's trajectory is essential. And the sequencing of actions, so the timing between your hands. So in this first analysis, we focused on that middle step, the prediction. And we basically asked in parietal cortex, known to be involved in visual spatial transformations and body space to real world transformations. Basically asking, does the parietal cortex represent the ball trajectory? Okay. So we did a straightforward analysis where we looked at the power before and after the ball's apex, the peak of the ball, which is known behaviorally to be a kind of very informative point in the ball's trajectory. So we looked at that, and of course each juggling throw, the apex is going to move around, okay, from throw to throw. So we did a simple regression analysis looking at the apex position, how that relates linearly to the power in the brain response at different times and frequencies. Okay, so you may be familiar with, there's EEG, ASR, and ICA. ASR is a noise reduction technique, so made a small change too. So this is a standard display of brain activity across different frequencies and time. So the point marked A is the moment of the apex. And so we see relative changes in power before and after the apex. But our question here is, how is that power, or is that power modulated by the throw-to-throw variation in the ball's position? Okay, because obviously that information is necessary to be able to plan the catch, right? You need to know where the ball is going to get the catch. So we found some pretty interesting results. So what this is showing now is not power, but it's the regression coefficient between power and ball's position, the lateral position. Okay. So essentially what this means is that rightward translations of the position at apex result in a reduction of power. And we've separated balls coming from the right, coming from the left. And this basically this mirror image we see on the opposite side of the regression coefficient tells us, not surprisingly, but according to this view of what the brain is thinking about, it's looking at the apex position in a midline symmetric sense. So, okay, so basically this is showing that the brain's response is modulated by the apex position. And that information is present from the time of the apex until the time of the next catch. Okay. The other kind of cute but actually deeply interesting part is we wanted to look at skill learning. And obviously, one thing that you can do when learning a skill is to slow things down. So the question was, how can we slow down juggling? Well, one easy way to do that would be to go up on the moon and juggle on the moon. So we created this VR simulation.
Then we were able to take our juggling experiment to well, together, virtual reality.
Okay, so as you can imagine, so I don't have time to go into details, but it's turned out to be very interesting. It does have some effects in learning, particularly the early stages of learning. Slowing things down does help people learn the sequencing of actions. So that's just shown there's kind of an initial burst of learning on day one compared to controls. And it uses this device called Spiders, developed by Dr. Sato at Tokyo Tech. And yeah, it's a 3D sort of haptic input device that lets you simulate throwing and catching balls. Okay, so back into sort of music, my interest has always been in terms of rhythm, and I'll maybe get across some of the reasons why. Okay. So some questions in our work are fundamental questions about why do humans dance and make music? Sort of, and one way to look at that is comparatively, looking at what sort of do we share with other animals. And to a neuroscientist, this essentially boils down to like, what kind of a brain do you need to be musical, to be able to dance? And if you didn't know, this is one study from the field by Charles Lim, looking at it's basically a study of improvisation. So it's looking at changes in blood flow in the brain, or blood oxygenation in the brain during improvisation compared to just playing scales by rote. And like for people studying the brain, music is just a very rich kind of cornucopia. It touches so many different brain processes. So that's kind of the motivation behind music and the brain. But I'm particularly interested in perception and how the brain sort of actively shapes what we perceive when we hear sound. And specifically focusing that down into rhythm. So whether when we perceive musical rhythm, is that purely an auditory function? Or as I'll explain quickly here, no, it's actually an auditory motor function. So hearing involves moving. So one of the questions about why music, and there are lots of creative ideas about why music, but one of the strongest ideas about and why rhythm, why dance and imitation is this. Our ancestors, they created bonds that were very time involved mutual grooming, right? Doesn't scale well at all. So the argument goes that, well, doing music together, dancing together is a bonding mechanism that scales much better. So if you take this to the extreme, this means that our musical and rhythmic abilities are what enabled human societies to grow from small groups to much larger groups. And of course, this continues today. We're bonded by music, anthems and other things. And so yeah, we see in all cultures have rhythmic behaviors, musical behaviors, often connected with dance. But they're often almost exclusively very social. There are ways for people to bond. So when we think about rhythm perception, there's the rhythm, which is the temporal pattern of events. So that's really the physics, the sound. And certain rhythmic patterns, the human brain gets very excited about when they have a sense of, so what we call beat. So rhythms that have, certain repetitive structure or integer ratios between the intervals, the time intervals. The human brain really latches onto that and can just get it in a way that we can't understand just random rhythm. So we have this thing called beat perception, which involves organizing time around a regular pulse. And it's, sometimes called chunking, right? So we're parsing time into sort of chunks of time. And it provides a much more kind of efficient way to conceptualize timing events. And so we've got this kind of hierarchy from rhythm, which is just a pattern, to beat, marking off regular times, to meter, which is a pattern of beats. And essentially it sets an origin and a scale for time. So when we perceive rhythmic music, we have this internal scaffold that says, okay, that's the downbeat, that's the one, that's where it starts, and this is the basic rate. So I've been just very interested in, what does that mean in terms of the brain? How does the brain do this? And the key point is that really this whole scaffolding for our perception of time is a creation of the brain. Okay, it's often suggested by the sounds that we hear, but it's essentially something constructed and under our willful control. So, take our message, the rhythm we perceive is determined not only by the sound we hear, but our internal sense of meter. So we started looking at that. And one way to do that is to kind of look at like kind of an auditory illusion of sorts. Take a fixed rhythmic pattern and basically induce people to hear it in various temporal organizations. So we're not talking about spatial rotation, we're talking about temporal rotation in a sense. So like a simple da-da-da-da-da-da swing pattern, okay? You can hear it with the beat, so to speak, on the first note, da-da, 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 or second note, da-da, 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 da-da. Okay, so the basic idea is the sound is fixed, but we ask people to hear it in these different organizations. And it's a, age-old technique in perception, but to say, okay, this is what lets us distinguish brain activity that relates to perception as opposed to just stimulus. Okay, so we've got two perceptual organizations of the same stimulus. And we found that the brain actually cared about that in the auditory system in the beta band. So the response was greater. The sound was marked as being on the beat. Okay, and very interestingly, that was only seen in the beta band. And as we did a control, which is where we actually physically accented the sound of the beat. So like we added a beat track to that. And so this kind of imagined beat causes the same types of modulation in beta band as the actual physical beat. Okay. So what this, tells us is that if we kind of very consistent model of sort of human auditory motor behavior, we've got, of course, our ear, which hears sound. We can parse this in various ways, but fundamentally, we have to have a link between the auditory and motor system to be able to dance or clap along or tap our foot with music. Okay. In humans, this is a pretty complex and flexible link, right? You can tap your foot, you can tap your left foot, you can snap your fingers, like very, very flexibly. We can kind of reconnect, sensory motor, different sort of outputs. But this last study showing that sort of something we do inside changes how things sound to us, sort of strongly suggests that there's also this reverse connection between motor system and auditory system. And so that's essentially what we've been studying. So that led us essentially plus this result, which is kind of a classic result, that if you put someone in an fMRI scanner and just look at oxygenation while they're listening to rhythms, and you ask them not to move, but just sort of listen and perceive the beat, you see auditory activity in the superior temporal gyrus, But you also see tons of motor activity, even when people are standing still. Okay. So the question is, is this motor activity just frustrated movement planning? Like, I want to move to this music, but they told me not to. But my brain is doing all the preparation for movement without actually executing the movement. Or there's something more. And we strongly felt it would be something more. So my colleague Ani Patel and I proposed the ASAP hypothesis, which is that the motor system is necessary for auditory beat perception. Okay. And this is based on a couple, pretty obvious things that the motor system is very good at creating temporal patterns. Okay. And so the idea would be that the auditory system uses temporal activity generated in the motor planning areas to basically scaffold its beat-based perception. So the signals, sort of the representation or the internal sense of where the beat is, it's not a great stretch to think that might be a motor representation, okay? Because we move in time with the beat. So we already do that. We move rhythmically. We proposed this dorsal auditory stream from auditory cortex through parietal cortex and premotor cortex. And of course, this would require bidirectional connectivity in that pathway. And we made a number of predictions, which I'll just briefly go through, a series of experiments over the past 10 years or so, trying to check off each of these predictions. So the first one was pretty straightforward. If we think the motor system is involved in beat perception, we ought to find beat-related activity in the motor system. The second one would be we should also find evidence for precise bidirectional directed signaling between auditory and motor, but motor and auditory as well. And then finally, well, if you really think the motor system for beat perception, if you interfere with the motor system in some way, you should affect beat perception. So straightforward. And these are all questions kind of in the, in the ability of human neuroscience at this point. Okay, so a slightly more weird experiment, but basically the same idea as before. We take a fixed stimulus, fixed rhythm, and we basically hear it in different ways to essentially align the rhythm and the internal sense of beat in different ways. And this gets back to kind of Terry's point, which is like, how do you study thought, which doesn't have like an external manifestation that you can time lock to? Well, in the case of rhythm, it's so crystalline that we can create this scenario. So we have a stimulus where the beat, marked in this number line, and the sounds of the rhythm are aligned. But we can also create rhythms in which they're shifted relative to each other. So here, the beat occurs before the sound, and here the beat occurs after the sound. And so essentially using the sound as our anchor to know where the beat should be relative to the sound, we can actually look for beat-related activity. And that's what's shown here. So here is a sound-related evoked response. And the blue and red are the two conditions where the beat is displaced from the sound, okay? So we can see that regions with this kind of response, they could care less about the beat. They just care when the sound happens. But we saw other regions that actually showed systematically shifted responses in these conditions, okay? So we can define that as essentially saying, well, that brain response cares about when the beat happens. It doesn't care about sound happened, okay? And if we classify them, each of these spheres represents an independent component from ICA analysis. And we can classify each one according to whether it cares about the sound, which is red, or the beat, which is blue. And sort of circumstantially, superficially, it matches this dorsal stream hypothesis very well with sound carrying units, sound carrying sources in auditory cortex primarily, and beat carrying sources in premotor cortex.
What about the PPC?
Yes, just thinking, should I say that or should I not say that at this point? Thanks for deciding for me. So yeah, PPC, I mean, anatomically, we know it's intermediate between those two. And we see kind of a mix of different response types in PPC. Still have to do this, but seems reasonable that there may be, there may be a transformation between this or mediation between these two different representations. Sorry, posterior cortex. Yeah. So AC is auditory cortex, PMC is premotor cortex, and PTC is parietal cortex. And so anatomically, this is called the dorsal stream. So there's not really direct connection between auditory and motor, but it goes via the parietal cortex. Okay, beat-related activity. This is a study by a grad student here at UCSD, Zoe Chang. Basically looking to see, looking for the connectivity question. So do we observe auditory motor connectivity? The experiment is kind of a modified version of that last one. We essentially have a rhythm that then gets a beat, and then the beat disappears. And so the basic idea is that if we look at the spectrum of the stimulus, we have energy at the beat rate in these two conditions, but then we have added energy at this meter rate, which is half of the beat rate in this physically accented condition. So we're going to compare these two situations, the same stimulus, but the task is for the person to hear this meter. In this case, it's in 2, 1, 2, 1, 2, 1, 2, and continue imagining that meter in this segment here. So we've got two segments where we've got the same stimulus. Here, they don't know what the meter is going to be. It could be 2, it could be 3. Here, they're actively imagining the meter. And then the question is simply, oh, sorry. Will we see some sign of this beat-related processing during the imagined meter? Yes, we do. So this is basically showing power spectra of brain activity. In the previous one, we showed the power spectrum of the stimulus. Here we're showing power spectrum of the brain. And we've marked off the beat rate as well as this meter rate, which is half of that in the Dubel condition. Blue is the baseline. Red is the physically accented condition, which clearly shows it mirrors the physical aspect of the stimulus. But yellow is the imagined meter condition. So essentially, we're seeing a sign of beat-related activity that's divorced from the stimulus. Okay, so something that the brain is essentially creating, and so we see something similar in this other condition, which is like more of a waltz. So just a variation. And we see that in both motor and auditory regions. So imagining the meter affects both auditory and motor activity. Just for the aficionados, I mean, we've got this MOBI technique that measures body movement. An obvious confound for this kind of study as well, like you asked them to move, but maybe they were like moving subtly. So we tried various techniques to measure EMG as well as movement to try to rule that out. It's difficult completely rule out, covert movement. But it's important to try. Most studies don't even try. And finally, looking at the connectivity, this is kind of going back to the method I talked about. We can essentially resolve in time and frequency information flow between regions. And the basic point here is we see, causal connectivity from auditory to motor, but also motor back to auditory. Okay. So that gets us this bidirectional connectivity, informational connectivity. And finally, there was the question about interfering with activity in the motor system, whether that affects perception. This is work done with Ramesh Balasubramaniam at UC Merced, who does a lot of work with TMS, transcranial magnetic stimulation, which is a technique using magnetic coils to induce current brain. And so there are various pulse sequences used in TMS. One called CTBS, theta burst stimulation, has been shown to depress activity in the cortex. They did this by stimulating the motor cortex and then seeing that motor evoked responses were smaller. So the game plan is simply do TMS over premotor cortex and over parietal cortex. And then we have a sensitive test of beat perception that we then do before and after the TMS to see, okay, does their ability to perceive beats change? And so we found for premotor cortex that this is a sham, which is essentially like a condition when the coil is turned upside down. So all of the other aspects of the stimulus, it's very noisy. So they're all kind of controlled for. And we saw, a modest decrease in the ability to perceive a beat. So this is essentially a task where you're listening to music and there's a beat track on the music. And that beat track will either be right, it'll be correctly on the beat, or it might be a little too fast or a little too slow. So in this case, they were doing worse at judging whether it was too fast or too slow. Parietal cortex was a little more subtle. It was actually a deficit in being able to tell whether the beat was a little too early or too late. And was only seen in people who are very good at this task to start with. So it's a bit more of a subtle effect. But again, both of those affirming at least, there is some causal role. Unfortunately, like in your dream, this technique would be like an on-off switch, right? Where you can just turn off the cortex. And it's not even close to that. It's pretty conservative. So the effects are often quite small. So kind of in conclusion, like we're just kind of going through and checking off these different predictions. But kind of the big picture circuits are working so far. Auditory cortex showing sound representation, motor cortex showing this beat representation. We saw tempo effects of beat perception when stimulating premotor cortex. We saw phase effects in posterior parietal cortex. However, there's a lot more to the brain than cortex. The basal ganglia and cerebellum are strongly involved. So that's kind of a limitation of this approach, that we're not able to really directly look at what's happening in the basal ganglia. So there are other approaches to do that. But yeah, the basic take-home message is beat perception is some combination of auditory and motor activity. So it's really, not really right to think of beat perception as being something that the auditory system is doing. It's more like something that the whole brain is doing. So there are many questions and ongoing projects. And I guess in my last couple of minutes, 2 more minutes, is that about right? Yeah. Okay, we're good. Okay. Yeah, just talk a little bit about directions we're going right now. One is to look at, there's kind of a strong story that interpersonal coordination is mediated by interbrain synchrony. Okay. And the question is, well, is that really a causal or exhaust fumes, the brain, as you mentioned? Because there are lots of common inputs and common outputs in the case of interpersonal synchronization. So is that interbrain synchronization simply a consequence of those common inputs and common outputs? So we've got some ideas about how to actually use another form of neurostimulation to essentially dial up and down interbrain synchrony. I'll just tell you a little bit about McMaster. We've got a lab, it's a Moby lab, but really for studying performance. So it's a concert hall that's been designed from the ground up to do scientific studies. So it's got basically a 100-seat theater. It's got virtual acoustics, motion capture for 100 people, and then EEG, eye, and physiology for people. And so the original idea was really to study, like, how does the audience respond to different musical activity? What is it about watching music live in a group that makes it different from just listening to a recording on your own? Those kind of questions. But we've had a chance this last year to kind of try to, conceive of this in a larger frame. And so we're really interested in just saying, well, just in general, let's look at how groups of people behave together, not just in musical situations. And so, there are many trends that have been talked about, but, the ubiquity of biosensing, the sort of, potentials of BCI for decoding brain state, and then a kind of constant desire for new ways for audiences to participate and engage in performances. And, the sort of science fiction, like, can we create new forms, new pathways for people to communicate with each other, okay, beyond this. There are a bunch of challenges that I won't belabor, but you know, these are things that we're trying to solve as well. Basically, the idea is to create like what we call large group mobile brain body to enable a study of large groups now in realistic contexts. So what if we could do EEG on 100 people easily? What if we can combine that with eye tracking and heart rate and other things? I mean, at the very least, you could do an entire like N of 100 study in one day, right? Which would be wonderful. But beyond, we can actually study people interacting. So a number of other modalities, emotion tracking, event cameras, and so forth. Combined with kind of some kind of real-time computing, so ability to estimate like a group brain and body state, okay? And then use that essentially to create, biofeedback experiments using this brain and body state to control the environment. And so that's this immersive theater. So we can essentially we can create closed loop feedback systems based on brain and body state that would affect the ongoing evolution of a performance, okay, as well as neuromodulation. And with some colleagues in Montreal, also very interested in comparing kind of live experience from other more technologically mediated experiences like virtual experiences or recorded video watching experiences, and how interacting with other humans versus virtual agents differs as well. So using this kind of lab setup to answer those questions is what they're very interested in. And finally, wrapping it all up in some kind of open science infrastructure. So this is kind of the vision of the future of the Live Lab. So of course, super interested in your thoughts and ideas about that, but also to say, if you have a burning idea that could really use a large group study, there's a place that we hope you can do that. So, all right, that's it for me. Yes.
So thank you. In your motor system, auditory cortex interactions, did you try to compare, a novice or just an ordinary person with a musician?
Yeah, good question. So I guess we haven't done that yet. Two of the studies I presented were novices, the first and the last. That middle one with the whole beat shift stuff, very difficult for novices to do. So that was all musicians. So the underlying question is, are musicians different, or are they just kind of part of a continuum? And for the most part, I can't answer that in terms of my own experiments. For the most part, most other kind of people that have compared them, it's a continuum, right? It's an elastic continuum. It's not like a phase shift. Like musicians are just different.
Well, but there's a perfect pitch. That's either you have it or you don't.
That's true. That's true. But it's not. Let's see, like how to say it. Like it, there is like. But there is evidence of learned perfect pitch.
Well, that's makes the point is that you can, when you learn it, you have it. You don't.
Yeah,
you don't have it, right?
Yeah. To be honest, there is actually even a spectrum of absolute pitch as well. Like there's some people with semi-absolute pitch.
Okay.
In the sense it's kind of like
some people have imperfect pitch.
Well, most of us have imperfect pitch. But like you can have sort of relative perfect pitch that's kind of anchored around. So yes.
The machine for
Yes.
is it motion capture or it's really
Yeah, sorry, I didn't explain that. Oh, sorry.
versus
It's actually they're ball-shaped grips that are suspended in this frame by wires. And those wires are connected to position encoders. So as they move around, you can then read out the 3D position of the hands.
close capture.
Yeah, I guess you could say it's motion capture. The device, it also has torque motors that can induce forces. And it needs those, first of all, to keep the wires from going slack, but then you can also simulate like pull. But yeah, it's sensing the 3D position of the hands. Yes.
So I noticed the rhythms that you had was about 2 to 3 to 4 hertz. Is
Yeah.
that correct? So
Yeah.
fairly low frequency.
Mhm.
So my question is, now that you know that there is this connection between motor and auditory regions for beat perception, can you predict or can you evaluate the extent to which we're able to perceive higher frequency beats?
Yeah. Yeah.
Does it correspond to our ability to move at that particular frequency? And then can we learn to overcome these limitations?
Right.
And does that propagate back to the motor system or back and forth?
Right. Great question. And Scott mentioned something about this earlier. It's well known that there's a pretty fixed existence range for this sense of beat. Roughly from 10 hertz, 10 hertz to about half a hertz to, every 2 seconds. Beyond that, events just sound unconnected. We can't link them into a flow. So on the fast end, yes, we can perceive faster than we can move. And that's been studied, you can tap every other sound. If the sound's 10 hertz, you can tap 5 hertz. So as far as overcoming that, I mean, certainly, Scott could weigh in about, skilled musicians, particularly, digital musicians, pianists. Sure, they can definitely move faster. There's some drummers who can train themselves to move really fast. As far as expanding the perceptual range of beat, though, I can't think of anyone that's like shown that really dramatically. That seems to be kind of a fixed limitation of the system. Yeah, it's a good question.
Do you mind translating? I'm a former professional ballet dancer, so I have a particular curiosity about the loop you described.
Mm-hmm.
Are there any behaviors that could either enhance or degrade that loop?
Right. Well, I think dance or music training, I would, hypothesize that that's enhancing that loop, right? That's what that training is. In particular, the way I think about at least some aspects of music training, it's also the ability to essentially like internalize that loop, in the sense that, like if you're starting to learn to dance salsa, for example, it's really hard to just do that in your mind. You need to move your body. But I think with enough training, certainly like musicians are trained to feel the beat without having to move to the beat, right? So to me, that's like a very important point to be made, like this ability to internalize movement, internalize the movement without having to move. And I think that's a key thing that's trained. I haven't thought about ballet per se. Do you have any thoughts about how this? Yeah.
I'm an engineer now, and I noticed that when I learned how to code, my dance got a lot worse. So it's interesting. There are certain behaviors where there are trade-offs in the brain.
Yeah.
So you're reaching some sort of global equilibrium rather than just local maximums.
Yeah, I don't know. I mean, it's an interesting question if there's trade-offs. There's certainly, abundantly clear that, that high-level performance ability in any physical field requires constant refreshing. Like you don't just get it and you've got it forever. You've got to keep. So that would be the sort of null hypothesis there. Is it just like, well, you're coding, so you're not dancing. So that's why, the dancing got worse. So.
Yes, I wanted to ask you about emotion and music. Inherently has a strong emotional response in some people. Different types of music have different, some people prefer different responses, different types of music. There's a big interbrain synchronization potentially component. It seems like people with some similarity, just by talking, synchronize their brain oscillations. Terry talked a lot about oscillations. I wonder if you, looked at either, can you predict what type of beat people like based on some other characteristic? Have you found some way to predict that they make similar brains like similar things? What's
Yeah.
the relationship
Right.
between emotion
Right.
and music?
Right. Yeah, I mean, I haven't studied that myself. Scott has studied emotion much more. But yeah, so there are some results from the live lab say that in a kind of music watching situation, that they were able to predict how much sort of let's see. So essentially it was a concert and there were some fans and non-fans, and they were able to sort of predict fanness based on the
They were-
correlation. They
they
were
were.
based on sort of inner brain correlation again. But is that just because fans are like more rapidly paying attention? Is it because they already know the song, so they're more able to train with them? There are lots of interesting questions that we need to dig into. I think Scott could speak. I don't know if your finding could ever be used to predict online someone's emotional state. What do you think about that from the EEG?
Yeah, I think so, actually.
Yeah.
Yeah.
Mhm. But that's definitely a big interest in sort of emotion decoding BCIs. And if you had that, I mean, you could do some interesting things about like there's a lot of people are very interested in understanding, for example, like interpersonal therapeutic relationships and the role of kind of emotional empathy and sort of emotional alignment in those situations. So it's not what I'm doing, but it's definitely a lot of interest.
There's, even among beetles, some beetles have different dances to differentiate between the, emerging different species.
Mhm.
So to be able to group different beetles that would otherwise interbreed to eventually be able to form a different species, probably we have a similar thing among, all mammals, et cetera.
Yeah.
And so
yeah,
music can be a way to differentiate,
right.
and so it's, we're not all the same. Interesting to be
Yeah.
able to find that in the EEG patterns.
Yeah, super interesting. Yeah, I mean, certainly like music is a way that we find kindred spirits, so to speak, right? Like, yeah, and difference is true. Yeah. So yeah, there's a like for some reason there's sort of persistent dream in the BCI community to have a BCI that suggests music based on your brain state, like on your emotional state and so forth. So that's something that I think people think would be good. So then you could say, okay, why not take it a step further and suggest me music according to your brain state? And that would be very interesting.
If you do it based on which song you listen to.
Sure.
So can you do it based on the EEG?
Yeah. In principle, why not? Right. Yeah. In practice, EEG is, complicated and noisy, but, people talk to TP, he's an expert.
Yeah,
in
we have built
BCI.
systems on FPGA.
You're building.
We have built a system like that on FPGA.
Would solve a lot of spousal arguments.
Yeah, I mean, yeah, the ultimate is like you have a little traffic light, red and green, right? Don't talk to me now. Beep.
One time I proposed that for music selection, which became a thing as the internet came on,
Yeah.
that you give people some sort of trackpad, or you could do it with their mouse actually,
Uh-huh.
and have them produce a rhythm, and not just, and then pick music, not just based on whether 3/4 or 2/4 or whatever,
Mm-hmm.
but based on the quality, the emotional quality of the rhythmic movements you're
Yeah.
making,
Right.
even on the micro scale, on the on the
Right.
mouse, with the mouse or the touchpad,
Yeah.
and then find music with that kind of pulse to it. And you remember Grace
I remember Grace. Yeah.
Leslie
Yes.
did an experiment where people tried to conduct the music that they
Right.
were hearing,
Right.
And we found there were brain associated with that. And only when she was when the subjects were fully engaged with the task.
Right.
So I presented it. I remember Taewon was here. We went over to someone who'd made a lot of money and had money to invest. And I tried to interest him in it was my only chance to, ask for lots of money from someone who was very rich. Yeah, probably. And it turned out he didn't know what I was talking about. What do you mean, move? How? And he had no idea what I was, the experience I was even talking about. Although, of course, it was, even then, there was a big industry trying to do music selection online because, of course, it has, it's so appealing to so many hundreds of millions of people. But so that remains to be tested.
Yeah. And I guess that connects with like emotion detection through movement analysis, right? Like, we can certainly tell someone's, at least some aspects of their emotional state based on how they move, right?
Yeah, well, Jeff Hinton showed that. He had the point light movies, where you put points of light on someone in the dark. And then he had people, you could, if you watch them walk, you can pick out a huge amount about what they're feeling, what their personality is, what they're, et cetera. There's excellent, including, and, but I mean, these very dynamic aspects. And so, and one of the early triumph of the deep neural network is that you could have the person continue walking past the recording without falling apart immediately in terms of communicating that using his wake sleep deep neural networks, and which was very impressive actually at that time.
Okay.
Yeah, as soon as you mentioned the link to the motor cortex, I was wondering if you had studied people with dyskinesia, like drivers, for example, and if this could be some sort of therapeutic method.
Yeah. So again, I haven't, but there's a lot of interest in using this essentially propensity to move in time with music for movement disorders, Parkinson's, stroke. There's a whole system of sort of music therapy based on like beat related music to help people walk more fluidly, for example. And there's another therapy for speech rehabilitation based on musical rhythms, for example. So yeah, I think it's a natural thing to think about. Yeah.
Thanks.
No.
Yes. Yeah. I wanted to go back to the Spotify playlist.
Okay.
And so one thing we see with the very large databases is that mood is one of the easier predictor, to tackle with EEG. So I do feel there is inter-individual. So, having like 20 data points for an individual, it can be predicted. I don't know about the noise, whether it's useful for his Spotify playlist, but yeah, I do feel there is potential for that in the future. Compared to psychopathology, it's like, which seems like much harder to.
Okay. So like sort of current
mood. Yeah,
mood.
positive, negative, these are parts of the EHR, electronic health record. They have to fill up all that information.
I see. So not like sort of like mood, how you feel today, not like this moment.
No, I can't remember the exact questionnaire, but I think it's how you're feeling right now.
Oh, right
it's
now.
Not
Okay.
how you're feeling today,
Okay.
because it's based on, repeated visits.
Okay. Okay, cool. And that's one of the easier things to predict.
Yeah.
So interestingly, you're saying EEG doesn't tell us a lot about pathophysiology, but sleep EEG does. And that's pretty obvious because often they have disrupted sleep. And so if you pick that up, you can pick that up early before the physical diagnosis that there's a hint that it's already progressing. The brain is progressing down that track.
Thanks.